So today I'm going to talk about performance tuning and just some of the kind of approaches and tactics you should take or undertake in order to performance tune as quickly and successfully as possible. Hopefully the crackling will stop a little bit. We will see. Right, so yes, as Bert explained before, I'm known as a diabolical developer. Everything I say is a lie, and you have to pick out what is truth and what is fiction. This is part of the fun of the talk. So boring stuff about me. The really important thing here is the third one on the list. We are building, as part of the overall Java community, a new build farm for OpenJDK, or Java itself. And we are going to produce LTS releases, so long-term service releases, for 4 years, 4 jaren, completely for free. And they will be tested, and they will be passing the TCK. So if you and your organization are concerned that you have to pay Oracle or IBM or another vendor a lot of support money for Java going forwards, then adoptopenjdk.net is the place for you to go. And it's a collaboration actually between a whole bunch of engineers from IBM, Red Hat, Oracle, Azul, Java user groups, so on and so forth. Hopefully that helps a little bit. So let's get into performance. So what is performance anyway? There are lots of different definitions out there. You can go to Wikipedia and there's sort of long and different articles about it. Looks like we're going to swap mics. Okay, we're going to swap mics. Give me 1 second. Right, so apparently now I'm not allowed to run around stage, which is a bit disappointing because this is a really cool stage to run around on. But never mind. So really performance tuning and performance is all about the sort of goals that you're looking for. What throughput do you want? What latency do you want? And by latency I mean, does the web page respond in 1 second? Does the messaging API respond in 10 milliseconds? Throughput is things like, can I push through 100,000 messages per second? And of course you've got your resource goals. How much money do I want to spend on Amazon? Who here is currently running on Amazon? Keep your hand up if you actually know how big your bill is. Yeah, it's a problem for the finance department, right? You just keep adding machines, it's fine. Right. So these are the 8 topics I'm going to cover. The first 4 topics, the eerste 4, are the important ones. Echt belangrijk, as they would say in Dutch. The following 4 are tactics that work today in 2018 with Java and the JVM. They may not work for your application. They may not work with Java next year. So take take the back 4 sections with a large grain of salt. A lot of cynicism required. So I'll start with the first bit. It's all about resources. I love Catan. I especially love playing children of around about the age in 8 or 9 because I always win. Pro tip, if you want to maintain your 100% winning record, play your nieces and nephews, that's great. And here is the problem with resources today. Today, just about everybody is on cloud or is moving to cloud. So I'm going to do a little poll here. Who here's production application is on a cloud server somewhere? So about half. For the people who are not on a cloud server, are you planning on moving to a cloud server this year? Just about everybody. Okay. So the problem with cloud is that cloud sucks. Cloud was designed by the big vendors to make you spend money with them. In terms of your actual application performance, in terms of your application deployment, in a lot of cases it's worse. It's harder than it used to be. And not only that, as a Java developer, you now get asked to run tools like Chef and Puppet and Ansible. I mean, that's shell scripting in Ruby, for crying out loud. Nobody wants to do this. And then they come up with this magical thing called Docker and Kubernetes, and before you know it, you're no longer a Java developer, you're a configuration expert. So it's really horrible. Probably the worst thing about cloud, though, is that you are on the open internet. So the beautiful 10 or 100 gigabyte connections you had in your data center, no more. If you're running on Amazon in particular, you have the joy of sharing the big pipes that come out of the Amazon data centers with Netflix. Now, who's the #1 network user in the United States today? You guessed it, it's Netflix. If your lovely application is sitting in the same data center in the same rack close to Netflix, guess what happens? You get nothing. You complain to Amazon and they say, well, you can buy a dedicated instance at 10 times the price if that suits your needs, sir or madam. And there goes your cost problem. So I won't talk to all the, I will let you read the slides and I will sort of vaguely talk to them and add extra points. So cloud is rubbish, so the uptimes are poor. In your data center, you're probably used to 4 or 5 or even 6 or 7 nines for uptime. You go to Google Cloud or Amazon or Linode or Hertzner or any of those providers, you're lucky if you get 2. So you need to build with resilience. Spinning up cloud instances, everyone talks about this horizontal elasticity that Amazon and others give you. It can take up to 30 minutes to get an Amazon server to start. Nobody knows why. Again, you just need to pay more. But this is the greatest point I want you to take home. You really need to understand what underlying hardware your virtualization is running on and how much virtualization you've actually been allocated. Case in point, we have one large banking customer who decided that it was a good idea to have 4 virtual machines of 32 gig RAM each, so 4 times 32, you can do the math in your head, on a 64 gig of RAM box. Now, I don't know about you, but even my 4-year-old nephew understands that 2 does not go into 1. However, many of you probably actually don't get visibility on the underlying hardware you're sitting on. And so you really need to work either directly yourselves if you're a DevOps pro organization, or with your system administrators to really understand exactly how the virtualized layer is being mapped to the hardware underneath. And it gets even scarier with Java, right? Especially with Java and things like Docker containers. So you may, for example, have a 512 meg Docker container. And so you think to yourself, great, I will allocate a 512 megabyte heap as the maximum. I see the wise person at the back shaking their head because he knows. He knows that Java actually also takes up a bunch of native memory, as well as, of course, the underlying container needs to have a little bit of memory itself in order to run its own operations. So you can't actually allocate a 512 meg heap. Otherwise, you start swapping. And we call it the cascading swapping disaster of doom. And the best one we've seen is when over 25,000 Docker containers were misconfigured in this way, and they took out 3 international data centers in one foul deployment. It cost that organization 21 million euros to repair, and they learned not to do that again. And it was just simple arithmetic that they were failing at. So pro tip number 1, know where your actual resources are. So if you're deploying to some cloud server, find out which country it's in, find out which city it's in, know where it is. This matters for your end users as well. And going back to the previous mini keynote from Uber, understanding your customers and where they might exist is actually really important in terms of where you host your application and which data center. We made this mistake. Most of our customers reside either in continental Europe or in London, and we stupidly put most of our data centers and our applications on Amazon West Coast. That wasn't very bright, was it? And all of a sudden, all of our users went, why is our latency so poor? Well, it's because we're sending messages across the pond for no reason. Not a good idea. As well as understanding where the hardware is, you need to understand how the virtual machines, and by this I mean things like VMware or other virtualization technologies, KVM, that sort of thing, laying on top of those pieces of hardware. And then if you're adding a Docker container on top of that, and this is the really fun game. So the fun game is you have the JVM, which is a virtual machine, sitting on a Docker container, which is virtualization technology, sitting on top of a virtual machine host, which is finally then sitting on some hardware. And each of those layers actually takes a little bit of CPU and memory and network I/O and disk I/O in order to manage itself. So you have to be careful at each layer going up that you don't over-allocate your resources. So always give yourself a little bit of room. And the room varies depending on what technology you have, but our rule of thumb is about 10 to 15%. Make sure that the underlying layer has 10 to 15% to spare so it can manage itself properly. So that's pro tip number 1. Right, so what is performance tuning anyway? So long list of explanations here. So we think it's understanding how the technology works, and for us, and this means how the JVM works, and most importantly, how the JVM interacts with the layer below it. So that would be either the container, the Linux operating system, or if you're really, really unlucky, Windows. Is anyone here still running Java on Windows? 1, 2, 3 people. You have my sympathies. I hope your bosses have given you a pay rise for the battle pay. Even Microsoft itself has said, if you want to run Java, run on Linux on our cloud. That's all you need to know. Shortly, I will show you something, what we call the Performance Diagnostic Model. This is what we use as a pseudo-scientific method to do our performance tuning, and it will dramatically speed up the time it takes to find the problem. And it's actually a proper methodology, and it's not sacrificing chickens or lighting black candles or hoping that Holland will get into the World Cup somehow, because that's just not going to happen. So that's the one thing that you can walk away from this talk with, is please use a methodology. Hopefully use this one, because we have proven it, but if not, then choose your own. And measure, measure, measure. Okay. When people just guess, it is absolutely pointless. You're just wasting your time, and you're wasting your team's time. Next bit, understand the architecture that you're working in. Who here has a massive poster of their architecture up on their wall next to their screen? Me. Yeah, cool. All right, so a good friend of mine, Simon Brown, who does some really great architecture talks, he always carries whiteboard markers with him, and wherever he goes, he either draws the architecture diagram on the nearest whiteboard, or he gets big A0 pieces of paper and he just sketches it out for the whole team just to be able to look at every day. And then understanding of requirements. So who here has had one of their users say, I want your application to be really fast? What on earth does fast mean? I'm going to go into what fast actually means for humans shortly. And unfortunately, you will need to learn a little bit of mathematics. In particular, you'll want to have a decent level of high school statistics, possibly first-year university statistics if you want to be really good at this stuff. And that's because you need to understand bell curves and standard deviations and things like linear regressions. Is anyone going to run away now? No? Who here loves maths? Yes, we all do. We're all computer people. Yes, good, fantastic. And last but not least, you want some tooling, because it's really hard as a human by hand to read through logs and understand what's going on. Note the sales pitch in the middle of the slide. My board told me to put it in. And a plan of some sort, right? You have design documents, you have testing plans, you should also have a performance testing plan. If you do not have one of these, and performance matters to you, you should have one, and start thinking about that. The whole goal is to remove bottlenecks, and you only want to remove one bottleneck at a time. And the reason is, you need to understand what the impact of removing that bottleneck is. As an example, your biggest bottleneck may, for example, be a thread pool in Tomcat that you accidentally set to a size of 1 when it goes and talks to the database. Well, that's clearly your bottleneck once you analyze that, and you increase the thread pool to say, oh, an arbitrary number, let's call it 10. And then all of a sudden your application gets slower. What's going on there? When you look at your overall architecture, you may discover that you are now flooding the database with too many calls, and it's just completely freezing up and it can't respond to your application. And this is again why you really want to fix one thing at a time, and you just take out the biggest bottleneck each time where you go. So, for that section, as a pro tip, make sure you get out those whiteboard markers, or if you really, really have to, find an old copy of Microsoft Visio. People remember that one, yes? Or use something like Google's Drawings or something that you can collaborate on, and make sure you get these diagrams drawn out. They're great for team bonding sessions, actually, when you start arguing about how your application really works. It's always entertaining. Next, I'm going to talk about time and time boxing. I'm going to have a fun experiment in the middle of this one. So you need to be really, 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 really careful about time, because you, as a human being, are really terrible at telling the time. And I'm going to do a little experiment now. I hope it's on the slide, not later on. This is going to be fun. So I would like everybody to close their eyes, count to 10 seconds, and then raise their hand when they think they got to 10 seconds, starting now. We have some early ones, we have some fast ones, we have one accurate one. Oh, and we have some late ones. So that range was about 6 to 15 seconds. This is just over a 10-second time window. So you can understand immediately how, unfortunately, how poor you are at timekeeping and at time in your heads. So humans have just zero capacity for this. So rule number 1, never trust yourself. You're wrong. Rule number 2, sort of trust the machines, but don't really. Every single hardware clock will give you a different answer. You can run this experiment in Java, call system.getNanoseconds on any piece of modern hardware, and do the division by 1,000 to get the milliseconds out, and do it for 1 second over lots and lots of loops, and see what the numbers you get coming out. Every different hardware and operating system combination will give you a different answer. So machines don't have a singular definition of time. And if you're lucky enough to have your entire cluster under the network time protocol, that can even make your machines go backwards in time, which is always fun for debugging. At a minimum, this is what you want to do with your architecture. You want to capture the time of a transaction as it goes in and out of every layer in your architecture. Here I present you your typical 1995 to 2005 architecture, the good old 3-tier, client, server, and database. And yes, you can see you just make sure you measure a point at 1 all the way through to 8. And that way you know where the time is being spent for each transaction. And there's lots of good tooling for this, right? You can use Datadog, New Relic, App Dynamics, jClarity's Illuminate. Other tools, you can use free tooling as well, right? You can inject your own timers. There's lots of free open source libraries. So make sure that you have these metrics being captured right at the start. Because if the problem occurs and you're not measuring these numbers, you don't know where the problem has occurred. And again, it's no point in looking it up. Who here is doing microservices and peer-to-peer applications? Ooh, only a few. Okay. So this is a brave new world. Some would say a stupid new world. So the problem with microservices is that you can't monitor them very easily. You can't manage them very easily. And in particular with performance, you've got no idea which service is really talking to which endpoint because there are gateways everywhere. And it's very, very difficult to understand where time is being spent. There is a vague new standard coming out called open tracing, and there's a competitor to it as well. So if you are using this style of architecture, or if you're going to go into microservices, you probably want to have a look at the open tracing standards and get those metrics into your application. If you really want to write your own simple timer, you can write something as simple as this. Or you can use Byteman, ByteBuddy, or ASM library to do some bytecode weaving and just weave timers like this into your code as you wish. So, that's the pro tip number 3. Make sure you have a timing measurement for your transactions at each entry and exit point in your architecture. If If you don't have these, then you won't know where the time is being spent. That simple. And it's almost impossible then to debug your application from a performance perspective. And now I'll get on to the important stuff. The performance diagnostic model. And it's this simple. You have actors, which are either human beings or other systems, pushing down on your application, so web requests coming in, JMS messages coming in, UDP or TCP packets coming in, that sort of thing. Your application code then executes and it pushes on the JVM, right? Garbage collection, just-in-time compilation, calls out to native libraries, I/O calls, that sort of thing. That JVM in turn pushes down on what we call the hardware or operating system level. So for most of you, it asks Linux to go do something, right? Linux may then ask a Docker container to do something or a virtualization layer to do something, and that might then ask some hardware to do something. But we sort of combine it all in one box. And that's the way you want to think about it. It's this sort of top-down flow of what we call pressure coming in from actors. And then we have this very simple flow chart. So I'll let you look at it for a while and I'll sort of explain my way through it. What you want to do is you want to start by looking at what the CPU is doing on your servers. If the CPU is doing what we call a system or kernel dominant activity, so it's doing lots of system and kernel work, okay, that means there's some sort of I/O operation, disk, memory, or CPU operation, which is being pushed really, really hard, okay? Or, if the CPU is being dominated by user time, then it's your application, or at least what we call your managed runtime. So it's either the JVM itself, so garbage collection typically, sometimes it's things like bias locking and things like that, or it's your actual application code or the way you've structured your application, which is incorrect. And then the one in the middle, the no dominator, which is surprisingly common, is when you have things like thread starvation, or a thread pool which is blocked, or deadlock threads, or you're waiting on the Facebook advertising system to return a call to you, because we're all here to sell ads, right? So I will come back to this diagram time and time again, so you'll get a fresh reminder of it every single time. But if you are into performance tuning, then this diagram, when you see the slide deck up on SlideShare later, print out a copy and stick it next to your desk. This is kind of the one that you refer to at 3 o'clock in the morning. And I'm going to go into some details here. So if you remember before, I said we want to look at what the CPU is doing. You want to understand if the CPU is actually busy or not. That's your first port of call. And you have a free tool to do this. It's called VMstat. It runs on every Linux operating system and just about every other operating system except for Windows, and nobody runs Windows, luckily. So who here has actually used VMstat on the command line? Wow, a surprising few of you. Okay, so homework for everybody else, run VMstat on the nearest Linux server to you, or on your Mac laptop, or even pay Amazon €3.45 and rent a server for half an hour and do it on there, and just start having a look at the output. And I'll show you an example of the output here. So the output has lots of different things in it. It has some details about what the memory is doing. It has some details about what the hard disk is doing, which is the BO and IN and BI, the BI and BO columns. And most importantly, it has the CPU information. And you can see 3 very interesting columns there. User, system, and idle. Ooh, you recognize these from earlier, don't you? User, system, and no dominator, or idle. Right, so immediately we can start mapping these things. So can people tell me whether this particular application right now, or this particular host right now, is it user dominant, system dominant, or is it idle? Idle, yeah? Okay, so if someone is screaming down the phone at you and they're saying your application is slow, it sucks, it's really, really poor performance, first thing you do is take a look at this. You have immediately eliminated lots of categories of problems, okay? It's not a memory problem, it's not a disk problem, it's certainly not the fact that your CPU is running hot, so it's not an application code problem, it's not garbage collection because the user isn't high, It's not a system or kernel problem, it's an idle problem. So immediately to yourself, you can start thinking about, okay, cool, so there are classifications of idle problems. There's things like deadlock threads. We could be waiting on a database call to return. We could be waiting on an internal queue to hand a message off to another queue inside our application. So instantly you've gone from 10 fields of haystacks to a single field with about 100 haystacks. But you've done that in the space of 30 seconds. Okay? Now I would challenge most of you to get to narrow down your problem space that quickly doing it via traditional means, which is, it must be that string concatenation, or it must be Hibernate, which is actually kind of true a lot of the time, but let's not pick on Hibernate too much today. Actually, I will later, because Hibernate is just evil. So, tactic number 4, what is your CPU doing? And with a little small proviso, at the time the problem was actually happening. So, don't have someone call you up and say your application sucked half an hour ago and then look at the CPU and go, oh, looks good to me. You need to be capturing that particular information, so the output from VMstat or the equivalent, you need to be capturing that 24/7. And again, there's lots of good free and cheap tools to do this. Things like Datadog in particular are pretty exceptional at acting as a metrics gatherer. So remember that. What is your CPU doing? Always ask yourself this. And now I'm going to go through the flowchart into all the different subsections, and then some of the sort of tactical things you can do to fix things along the way. So, if more than 10% of your CPU, if your CPU time is doing 10% system time over anything else, so basically just look for a high number in system, or look for a number in system which is equal or higher than user, then you've got a system or kernel problem. And it's going to be one of about 4 things. Either the CPU is busy context switching, the operating system is busy context switching, and by that I mean you've either got multiple applications or your JVM having threads fighting over the CPU. So it's like one thread goes, I want the CPU, and the Oracle database in the corner says, I am Oracle, I am owned by Larry, I own all the CPU. No, I really own all the CPU because you are being charged on a per CPU basis. If you are still in the habit of sharing a data store on the same host as your main application, especially a Java application, just be aware that almost every data store on the planet is incredibly greedy when it comes to using CPU. So you typically want to split those things out, architecturally speaking. It could be disk I/O. So we've seen many cases where, for example, it was good old log4j misconfigured, writing 100 meg per second to disk. So all the operating system is doing is going, I'm writing to disk, I'm writing to disk, I'm writing to disk, I'm writing to disk. And your application thread's going, I'd like to calculate that important tax number, please. The operating system goes, nope, I'm writing the debug message to disk. It gets even better. If you're in a country like Australia, which is very, very wide, about 4 time zones, and your log4j configuration is not only just writing to disk, but writing to disk on the other side of Australia, then your log4j messages are going up to a satellite, all the way down across to Perth, look it up on a map, and not only do you destroy the disk on the other end, you destroy the network bandwidth, and you piss off your satellite operator as well. A very large Albert Heijn equivalent in Australia did this for a good month or 2, which was highly entertaining. And there's some more things there as well. So if you see that you are system dominant, so that little column which had the S label on it, then start looking for these sorts of things. And the free tooling you can use and the data you can capture, again, is just listed there. Right? So you've got VMstat, IOstat, NetStat. Just make sure you're capturing those 24/7, and you'll very quickly see what's going on. And just to quickly sort of go over this again. So if it's a memory issue, like for example, the Linux operating system is paging memory in and off the hard disk because you've asked it to do too much, read in too much memory, you'll see things like the memory numbers start going crazy, and the swap columns, SI and SO, will start going into the thousands. Right? If it's a hard disk issue, you'll see the BI or the BO, which is read and write, columns, they will start to go into the thousands. If you're flooding the network, you'll see things like the IN, which is the interrupts column, that will start going into thousands or tens of thousands. And the CS column, that's context switching. And if you see that go into, say, 5,000 plus, then chances are that's your problem. So you just basically look for the big number in the column, which is the pointer to where the problem is. Right, so we talked about that being there. Let's just go back. I had these slides the wrong way around, I apologize. So this is the slide I should have shown you first. So a reminder for the diagram. We've taken a look at what the CPU is doing. The CPU is system or kernel dominant, so either the amount of system activity is more than 10% of everything else, or it is greater than or equal to the user activity. Okay? If that's the case, go look at those other tools, see what's going on. And command line tools are probably the best way for you to learn this to begin with. So you can run vmstat, iostat, and netstat. You can just run it in a terminal shell window, and you can just run it forever. Then just do something mean to your application, like ask Hibernate to do a cascading delete, or set log4j debug to trace, something like that, and you'll start to see this activity coming through. Right, I should have swapped these around. The next one we're going to look for, if it is user dominant, so if the U column in the CPU was the highest number, then we need to look at two things. Either it's going to be the JVM or it's going to be the application. And we want to do the quickest interrogation possible to find out which one of these two things it is. Oh, my slides are all over the place today. Interesting. This will be fun. Let me go back here. Boom, boom, boom. Okay. I'll just go back one. The best and quickest way to find out whether it's a JVM problem or an application problem is to look at your garbage collection log. So the biggest impact a JVM normally has on your running application these days is garbage collection. And there's a whole other talk as to why that is, but very briefly, because Java is being asked to work in microservices and really small heaps, as well as being asked to work in really big heaps, like 100 gig plus, Java just wasn't designed to do that. The garbage collectors that we have today just don't work very well under those circumstances. So for most applications today, garbage collection is a serious problem, right? Lots of long pauses. So make sure you turn on your logging. These flags are for Java 8 and below. For Java 9 plus, the flags are a little bit different, so I will make sure I update these slides before I push them out. And you can use a GC log analyzer to figure out what's going on. Now, our one, of course, is a reassuringly expensive paid-for commercial tool, but there is also GC Easy and GC Viewer, which are both free tools to use. So you can remember those. So GC Viewer and GC Easy. Okay, those are free tools to use. You can use our tooling free on trial as well. And what we want to do is we want to take a quick look at 4 or 5 different pieces of data in the GC log to see whether it is a JVM problem or whether it's a user problem. And again, what we're trying to do is to narrow down where the problem is as quickly as possible. So if you remember to begin with, we only took 30 seconds to look at vmstat and go, right, it's either system, user, or idle. Okay, so we've only spent hopefully a minute or two so far. This will take about another 5 minutes. So hopefully within 10 minutes we'll know where we're going. Right. So you may see things like this. There is a pause time there of 42 seconds. Pretty obvious candidate. The best one we've seen is 62 minutes. That was really fun. So that is your JVM, Java, pausing completely. Nothing goes forward. Nothing works. It stopped the world for 42 seconds. Clearly, garbage collection is at fault here, and you can start doing deeper analysis to figure out why. You may have very poor throughput So this is a percentage graph of how much time the JVM is spending doing garbage collecting, so just doing maintenance work, as opposed to letting your application do its work. As you can see on this graph, the percentages are very, very high, almost up to 100% towards the end there. So this JVM, the only thing it is doing garbage collection. And your application is actually doing nothing. Again, another indicator of a problem. Here we have how much of your heap do you have left after garbage collection takes place. Here we have back-to-back full GCs happening every 0.1 of a second because we've basically run out of room. Okay? Our maximum heap just simply isn't big enough. So this would be a really easy fix. Just double the size of the heap, run the application again, and hope you've got enough room. Okay. This is actually not a memory leak, by the way. I'll show you a memory leak next. Or will I? Yes, I will. Cool. This is what a healthy application looks like. If you see a graph like this, shut down the tool, go back to the flowchart, you're going to go down the application path instead. Okay, it's not a JVM problem, most likely not. If it's a memory leak, it's going to look a little bit like this. What you want to do is you look at the bottom of the graph and see how it trends upwards to the right. In about 3 weeks' time, this very important trading application at an unnamed investment bank is going to have a very bad day and is going to cost that bank a lot of money. So this is what a memory leak looks like. Most of the time, people do have memory leak issues, and luckily there is some good free tooling on how to find memory leaks. So what you want to do is use Visual VM, which with Java 8 and below comes with Java itself. Java 9 Plus, Oracle helpfully removed it, but it's okay because you can go to visualvm.net or visualvm.org, I think, and get a copy from there. And this is what you do. You say, I want to do some memory profiling, please. You'll notice there's a little settings checkbox in the top right-hand corner. Make sure you tick that settings box. And there'll be another button under there called Record Allocation Stack Traces. And what this will do is it will tell you which line of your code is creating all of those char arrays. And you'll notice the char arrays have lots of generations, 91 generations. And what that's telling you is that they're constantly being created and they're not being deleted. They're not being garbage collected. So that is the definition of a memory leak. So basically look for the big red bar at the top, click on Settings, click on Record Allocation Stack Trace, and you'll get a lovely diagram like this. And we've highlighted the line in our Hawkshaw application, which is the thing which is causing the memory leak. Now, if anybody tells you, oh, it's Java itself which is memory leaking, they are almost certainly wrong. It is always your fault. It's always your application's fault. So make sure you record the allocation stack trace and you turn that on. A word of warning, when you're using a memory profiler like Visual VM or any other, and you put it onto your production machine, you are going to slow your production machine down. So of course, because you are all good DevOps teams now, aren't you? Yes, good. You have an exact clone of production, don't you? With the same traffic and the same patterns. Yeah, good. This is what Docker and all the DevOps tools are all about. You should be able to clone your environment exactly. But in all seriousness, you should at least in your CI platform make sure that you run a load test or something similar and use the tooling there instead to go fix the problem. Enough of a sales pitch. So, either we went and solved the garbage collection problem, especially if it's a memory leak. There are lots of different ways to solve garbage collection problems. It's another 2-hour talk. I won't go into it. We have lots of free slide decks on SlideShare for that stuff. So we'll go to the fun one. We'll go to application. So when it's application dominant, what we're saying is that the CPU is running at almost 100%. It's not garbage collection. It's actually our code, which is asking the CPU to do lots and lots of work. It's almost never the fact that you've got a slow algorithm. So a lot of people like to sort of optimize their Java source code, thinking that, oh, this will help the JVM. It won't. The JVM and the 10,000 person hours that have gone into it has ideas and technologies and ways of looking at the runtime information which just no human can comprehend unless you're Cliff Click, the original author. And we interviewed him last year, and he can no longer read his own source code. This is a problem, and this is why Java is going to replace Hotspot with Growl at some point, because we can read the source code, which helps. But typically what you want to do here is you want to use an execution profiler. So previously with the memory issue, we were using a memory profiler. Here we want to use an execution profiler. Visual VM, that lovely free tool I mentioned before, is also an execution profiler. Hooray. So we can just use that. Go past that one. Just very quickly, I'm going to rattle through these slides because we're a little bit short on time. The reason why you don't want to prematurely optimize your code is because Hotspot is far better than you at doing it. This is a tiny subset of the optimizations Hotspot does for you. There's over 600. The big one it does is it does method inlining. And method inlining means if I am class A with a method and I am calling a method in class B, and that method is small enough and optimized enough and called often enough, I will just haul it into my class under the hood. And now I have a larger block of code I can do all sorts of other interesting analysis on. And so that's what kind of happens under the hood. So you can see it can do all sorts of interesting techniques. I won't bore you with all the details. The methods to be inlined must be 35 byte codes or less. Okay, this is the one important thing. So when people tell you to write small methods that do one thing and one thing well, it's not just good solid principles, it's not just good design principles, it's actually good for the Java's performance by default. Here's an example of what the JVM will do with good old FizzFuzz. Who here has had to do this in an interview? Did you pass? Yeah, good. So FizzFuzz, count from 1 to 100 for divides by 3, print fizz, 5 fuzz, 15 FizzFuzz, right? Or print out the number. So your typical Java engineer would probably code a solution which looks a little bit like this, and some methods like this, right? Nicely split out, small methods, so on and so forth, very verbose, but fairly typical Java of today. The just-in-time compiler would turn it into that, okay? Which is probably what any other sane developer in any other sane language would do anyway. But the just-in-time compiler will actually compress it even further than this, believe it or not. There's some other tricks that it performs to make it even faster than just this subset of code. So you can write all the lovely verbose Java code you want with nice static typing and good variable names, which means it's readable, it's understandable by the end user, and the JIT will actually take care of the performance for you. So don't worry about that. Here's another fun trick. So we always like to say that Java can create objects 1 million per second at 0 cost. Can anyone tell me how long they think this measurement will be? 0. Okay, correct answer. People have seen this trick before. Because O does not escape the for loop, the just-in-time compiler says, well, O is never used, so I'm just going to dead code eliminate it. Oh, that for loop doesn't do anything now, I'm just going to dead code eliminate that. Oh, that object O declaration, don't need that anymore. So 0 minus 0 equals 0. Great, done. We're done here. Fantastic. Be very, very careful if you are micro-benchmarking yourself. Do not ever micro-benchmark yourself, because you'll fall into these sorts of traps. So the Netbeans execution, or the Visual VM execution profiler, again, you can attach it to your running application in the mirror of production that you see. And big red bar is the thing that is using up all the CPU. Remember, click on the settings checkbox, print the allocation stack traces, or sorry, the execution path, I think it's called, or method profile path, and it will tell you which line of your code is causing the JVM to do all this CPU work. If you want to understand if your methods are 35 byte codes or less, then get the tool called Jitwatch, which is completely free. It has this awesome 3-column layout, your Java source code, the Java bytecode, and then the machine code. Yes. And what you can do is you can print out the machine code and stick it up next to your wall, so whenever your boss walks past, they understand how deeply technical you are. It's good for pay negotiation. If you are going to do benchmarking, you must use the Java MicroBenchmark harness by Alexei Shiplev, who used to be the head of performance for Java at Oracle and is now the head of performance for Java at Red Hat. He makes sure that things like the little trick of object O being eliminated and things like garbage collection interfering in your benchmarks gets taken care of in his framework. So you can use annotations and other method calls using JMH to make sure that what you're measuring is actually the true measurement. So please do not micro-benchmark yourself, use JMH. It will also give you those lovely statistical graphs I talked about earlier. I have to start going pretty fast now. So, in short, if it's application dominant and your code is running really, really hot, make sure you write the solid code so stuff can be inlined and stuff can be jittered correctly, and that'll help speed things up. And if you absolutely have to, use Java MicroBenchmark framework and Jitwatch to understand and optimize those hot paths. All right, and I've got about 4 minutes to go through 10 slides, so we're going to go really quick now. The last bit is the nothing dominant. So CPU is not using user, it's not using system, it's effectively idle. All right, so what do we want to look for? We want to pull out Wireshark. For the first half hour, you'll use that to spy on what your neighbor's viewing on Netflix. And once you've stopped having fun with that, and once you've taken yourself off your intelligence agency's watch list for even downloading Wireshark, you can start to understand what all of the network connections in and out of your application are doing, and whether they're just sitting there doing nothing, or whether they're actually sending traffic or not. So Wireshark, again, great free tool. It could also be an internal threading problem to Java, and as you can see, the thread state model in Java is simple. If you really wish to understand it, you need to read the Java memory model section in the Java and JVM language specification, which will definitely help put you to sleep. Also buy Brian Gertz's Java Concurrency in Practice, and make sure you go into Heinz Kibutz's Java Specialist newsletter where he teaches concurrency. But again, you can actually pull out Visual VM or the NetBeans profiler, and you can say, what are all of my threads doing? Yellow is waiting, green is go, red is blocked. So if you remember all the way back, if your CPU column is saying idle, and you go and have a look at your thread pool, and your thread pool is mostly yellow or mostly red, then you know exactly where the problem is, right? It's either waiting for traffic to come in, or it's gone and deadlocked itself on something. The NetBeans Thread Inspector, or the Visual VM Thread Inspector, will actually do deadlock detection for you, and it will also tell you exactly what Java source code the lock is waiting on. So again, it's a free tool you can just grab. There you go, deadlock detected. You don't even have to figure this stuff out yourself anymore. It's very handy. So Visual VM and NetBeans are both good, free, adequate profilers. Eclipse MAT is a memory profiler. There's a profiler that comes with IntelliJ. You can buy JProfiler. I'm being told this is the end. Or you can go for some really expensive commercial tooling. But my word of warning is that all of the profilers lie to you a little bit, because they have to do statistical sampling, and sometimes they have to ask the JVM to stop in order to get their statistics out. Okay, so some of you may have heard that Oracle's Java Flight Recorder has recently been open sourced. That is actually the best source of truth when it comes to this stuff, and so from about Java 11 onwards, you'll actually be able to get the data out of Java Flight Recorder for free, and that will be the best tool you can use going forwards, and I'll update my talk then. So don't tune by folklore. Try and tune using the methodology that I showed you, right? Go through the flow chart, and then as you go down each path, there's a whole bunch of tools that you can use today to figure stuff out. We're doing a whole bunch of stuff to try and help at the moment. Go past that. We have no time for questions, which I love, because then no one can ask me anything awkward. But do come see me afterwards. I'll just be down over there, down the right-hand side. Thank you very much for your time. Don't forget to go there to keep me fed. And I hope you have a wonderful afternoon.